Thank you very much, Teresa. We are focused on helping our customers get the best possible pH data, so we will keep today's presentation very practical. It will focus on measurements in the lab, but if you want more information on field pH measurements, we have a previously recorded webinar on how to obtain high-quality field pH data. Please check it out on our YouTube channel. We will begin with a short discussion of how a pH electrode actually works. After establishing these basics, we will discuss the different structures that make up an electrode, which will then lead us into electrode selection. Perhaps the most practical portion of this webinar will be focused on calibration, measurement, maintenance, and storage tips. After selecting an electrode, these tips will ensure the data you collect is accurate and repeatable. We will wrap up with the most important questions you should ask when selecting a pH meter. And then I will also go over some resources that we do have at YSI. pH measurement with a glass pH electrode relies on the measurement of a voltage. In order to measure the voltage, 2 points with different electrical potentials, basically electrical signals, are required. The reference electrode is designed to maintain a constant potential that is independent of the sample. The reference is sometimes referred to as a reference half cell. In contrast, the sensing portion of the electrode, sometimes referred to as the hydrogen ISE, or a sensing half cell, provides a potential that is dependent upon the sample pH. The millivolt output seen on the pH meter represents the difference between these potentials. This measured voltage is correlated to the pH of the sample based on the Nernst equation. Therefore, both the reference electrode and the hydrogen ISE are needed when determining pH. The reference electrode and the hydrogen ISE can be separate electrodes, or they can be combined into a single electrode for convenience. The combination style electrode is used in about 90% of all pH applications, and all YSI electrodes are of this combination type. A pH electrode consists of several structures, each of which can be seen in this figure of a typical combination electrode. The main components are the electrode body, the glass pH sensor, the reference electrode, the reference electrolyte, and the reference junction. It is important to understand these structures before choosing an electrode, as some structures can vary from electrode to electrode. Your application will determine the characteristics your electrode should have. The term glass pH electrode is commonly used, but this description is simply referring to the material used to construct the sensing portion of the pH sensor. Glass pH electrodes can have either a plastic or glass electrode body. Field electrodes typically have plastic bodies, as plastic body electrodes are more rugged than glass body electrodes. YSI offers both glass and plastic body electrodes for the lab, with glass electrodes having a greater range of operating temperature. Glass body electrodes are also frequently used in more challenging samples, such as very acidic solutions, where plastic body electrodes are not suitable. The glass used to construct the sensing portion of the electrode contains alkali ions such as sodium or lithium. These ions, along with hydrogen ions in solution, form a very thin gel layer on the inside and outside of the glass. The gel layer is in dark blue on this image, while the glass pH sensor itself is in light blue. This layer acts as an ion exchanger of hydrogen ions, as alkali ions from the gel layer are exchanged for hydrogen ions from the sample. Therefore, depending on the pH of the sample, hydrogen ions will move into or out of the gel layer. With the pH electrode, the glass pH sensor, sometimes referred to as a membrane, is fused to an electrode shaft. The inside of the sensor is filled with the buffer solution of known pH, commonly pH 7. This electrode design creates an environment with constant binding of hydrogen ions on the inside of the glass sensor, while the outside of the glass is exposed to a sample or to the sample where a variable amount of hydrogen ions exist. The difference in pH creates a potential across the glass pH sensor that is compared to the stable potential of the reference electrode. The glass pH sensor shape can vary in order to meet application needs. Sphere, otherwise known as bulb-shaped sensors, as well as cone sensor shapes can be used for most applications, but unique applications may require a specialized sensor shape, such as the spear-tipped YSI TrueLine 21, which can penetrate semi-solid samples such as meat, and the YSI TrueLine 27 with the flat sensor that can be used for surface pH measurements of items such as paper. This table provides an overview of the different types of glass pH sensor shapes. Now, moving on to the reference electrode. There are different types of reference electrodes, but we will focus on 3 here. The mercury chloride reference electrode has been in use for the longest time. It has a very stable potential, but it is rarely used due to the toxicity of mercury. Also, the reliable temperature range when using mercury chloride is relatively narrow. The most common type of reference electrode used today is the silver-silver chloride reference electrode. Since silver is non-toxic to humans, silver-silver chloride electrodes can be used in medicine and food technology. Disposal is also less critical with these electrodes compared to mercury. Silver-silver chloride has a wide range of applications, and most YSI lab and field electrodes feature this type of reference. The iodine-iodide system is a relatively new reference electrode that has several important advantages over other electrodes. This reference is metal ion-free, which is very important when measuring in tris buffer and protein solutions. Reference electrodes like silver-silver chloride have metal ions that will negatively interact with these solutions, resulting in the reference junction becoming clogged. The iodine-iodide electrode also has a low temperature dependence that allows for rapid response time. Also, the stability of this reference, even at changing temperatures, results in excellent measurement stability. The unique color of the YSI iodine reference can be seen here on the right. At this point, I did want to further clarify the interaction between the reference electrode, reference electrolyte, and the junction. The reference electrode is placed in a solution of reference electrolyte that has contact with the sample through the reference junction. Therefore, the electrolyte has a connection to the sample through the junction, as it serves to close the electrical circuit in the electrode. A reference electrolyte must have certain qualities. It must have good electrical conductivity, and since some electrolyte will leak into the sample during measurement, it is also important the electrolyte not react with the measurement solution. The ions of an electrolyte solution must also be equally mobile. If they aren't, unwanted potentials can develop, resulting in poor results. Potassium chloride, or KCl, has all of these qualities, so it is by far the most commonly used electrolyte solution. Some applications require specialized electrolyte solutions. For example, a customer may need electrolyte that is completely chloride-free. Therefore, other electrolyte solutions can be used, but only if the electrode manufacturer specifically states that other electrolytes besides KCl are acceptable. Our YSI iodine can make use of these other electrolytes. Now, the form of KCl can vary. Gel electrolyte still consists of KCl, but a gelling agent is added in order to prevent the electrode from losing electrolyte too quickly. Since they cannot be refilled, electrodes with gel electrolyte are easier to maintain, but they do have a shorter lifetime than those with liquid electrolyte. Field electrodes are typically gel-filled. Electrodes with liquid electrolyte can usually be refilled. This results in a longer electrode life. It also allows the user to easily refill the electrode when needed, as well as replace the electrolyte if it does become contaminated. Response time of the electrode is typically faster, and the measurement signal is more stable if liquid electrolyte is used. Faster electrolyte outflow from these electrodes also helps to reduce troublesome diffusion potentials that may develop, and it also ensures the electrode junction doesn't become easily clogged. If you were in the lab, I would definitely recommend an electrode with liquid electrolyte. All YSI refillable lab electrodes use 3 molar KCl for the reference electrolyte, but other manufacturers may use slightly different forms. One important tip I did want to mention is that if your electrode is refillable, it is very, very important to have the refilling opening in the open position during calibration and measurement, as you can see here. As was previously mentioned, the reference junction, sometimes referred to as a salt bridge, creates contact between the reference electrode and the sample. Like the reference electrolyte, the junction needs to have certain qualities. It must be permeable and it must allow a consistent outflow of electrolyte. Now I do want to mention that there is a variety of junctions offered by manufacturers, but we will discuss the most relevant YSI junctions. The ceramic junction uses the porosity of unglazed ceramic. This type of junction can easily become blocked, and its low rate of electrolyte outflow can result in the development of disruptive potentials. Although this junction is not good to use in solutions with either high or low ionic strength, it is good to use in solutions that contain oxidizing substances. The platinum junction consists of fine, twisted platinum filaments between which electrolyte flows. This junction type features a constant outflow rate of about 1 milliliter per day, and it does not easily become blocked. Care should be taken when cleaning this type of junction, as it is susceptible to mechanical stress. The platinum junction can be used almost universally, so it is the electrode I would recommend for most lab applications. However, for solutions with a lot of solids, low ionic strength, or high ionic strength, the ground joint junction is the best to use. This electrode junction features a much faster outflow of electrolyte, and it is very easy to clean. This junction, also known as the ground glass sleeve junction, features 2 ground glass surfaces mated to one another. These 2 surfaces fit tightly together, but they allow electrolyte to permeate between them. The outflow rate can be adjusted by moving the outer glass sleeve up or down. YSI field pH electrodes feature the Pellin strip junction. A strip of Pellin, which is a non-woven nylon-like material, is held in place by a silicone bushing. Just like other field electrodes, this electrode features gel electrolyte. It is possible for the reference to become contaminated. In order to help prevent contamination, or at the very least slow it down, some electrodes feature additional internal junctions. With these electrodes, the reference is placed within an extra internal chamber. This chamber also has a junction in order to ensure contact between the reference and the sample. This extra chamber is very effective in serving as an additional barrier to contamination. Many YSI electrodes feature a double junction design, and our ioline even features a triple junction design. Now, all of the information we just covered can be used to help you select the best electrode for your application. Now, a common question asked is if a single pH electrode can be used for every application. The answer to this is no, because sampling applications and requirements can vary dramatically between applications. As an example, measuring in meats and cheeses will require a spear tip sensor, while surface measurements require a flat sensor. If measuring in tris buffer, an electrode with a metal-free reference is required. The most important consideration when selecting an electrode is your application. This will help determine the shape of the glass sensor, the junction needed, the reference electrode, and other important characteristics such as electrode body. In addition to considering the application, Users should also consider convenience. All pH measurements need to be compensated for temperature. So rather than having a separate temperature sensor, it is most convenient to have a temperature sensor built into the electrode. An electrode with a temperature sensor, reference half cell, and sensing half cell all in one electrode body is sometimes termed a 3-in-1 electrode. A large number of YSI lab electrodes feature a built-in temperature sensor. It is also important to consider the likelihood of the electrode being banged around in the lab. If this risk is high, perhaps it is best to go with a plastic body electrode. Also, if you are concerned with the electrode being properly maintained, it might be best to get a gel-filled electrode, as they do not need to be refilled with electrolyte. However, if you would like the electrode to have a faster response time and a longer life, a refillable electrode is the way to go. If ordering a refillable electrode, don't forget to also order some replacement KCl solution. It will definitely come in handy. To help you select the best YSI lab electrode for your need, or if you just want to learn more about the different electrode structures, please check out our lab electrode selection and application guides. Please don't hesitate to contact us if you have any questions about these tools. With that, I would like to hand it over to Laura to discuss some practical pH tips.
Thanks for the great overview, Chris. Good afternoon, everyone. There are so many options when it comes to selecting an electrode, so be sure to check out the selection guides that Chris referenced. If you have any questions about which option would be best for you, let us know, and one of our technical application specialists can assist you in selecting what would work best for you. Now I would like to review some calibration and measurement recommendations to ensure you are getting accurate and repeatable pH measurements, as well as maximizing the usable life of your electrode. Let's first address calibration. The absolute best thing you can do to obtain accurate, repeatable measurements is to ensure you are performing a good calibration on your pH system. The system includes the meter and the electrodes. Let's talk about the two major system types available, which are analog and digital. Many newer instruments are digital and utilize digital smart sensors. For these newer instruments, the calibration is stored on the sensor and digitally sent to the instrument. In this case, you can remove a calibrated sensor and place it on a different instrument without recalibration. On the other hand, it's important to remember that many instruments in use today are of the older analog type. In this case, it is very important that you calibrate the sensor and meter as a system and keep them together, since the calibration is stored in the meter in this instance. In the end, regardless if you are using an analog or digital system, your data is only as good as your calibration, so be sure to take the time to do a proper calibration. So, what are we actually doing when we perform a calibration? Chris previously discussed that we calculate pH based on the established linear relationship between pH and the sensor's millivolt output, as defined by the Nernst equation. In order to apply this relationship to the electrode's output, the instrument must be calibrated properly using buffers of known pH values. During the calibration, the sensor's millivolt values and the pH buffer values are used to establish the electrode slope and intercept, or sometimes referred to as 0 point or offset, of the plot of millivolts versus pH. Once the system has been calibrated, the pH millivolt output of the electrode in any media can be converted by the instrument software to a pH value. We will define the practical limits of the zero and slope again later. Let's discuss why it's important to accurately measure temperature when calibrating and measuring pH. During calibration, we establish the slope and intercept of the millivolts to pH units plot at the temperature of calibration. In order to accurately make pH measurements at temperatures that are different from calibration, we need to adjust the slope and intercept of the plot for the temperature of the sample. The Nernst equation allows for this temperature-based adjustment, and this is carried out by the instrument software. All you need to do is be sure that you are accurately measuring temperature during calibration and subsequent measurements. With today's pH systems, you have some options for measuring temperature. The best option is to select a pH electrode with a built-in temperature sensor. When pH electrodes have a built-in reference electrode and temperature sensor, they are commonly referred to as a 3-in-1 sensor. The next best option is to supply a temperature reading directly to the instrument via a standalone temperature sensor. Most meters allow you to directly connect a temperature sensor. You can make sure this temperature sensor, you just have to make sure that this temperature sensor is in your buffers during calibration and in your sample during measurement. Some meters allow you to use a temperature reading from a different sensor. For example, on the YSI multi-lab, if you have a different probe installed, for example, a conductivity probe that also has built-in temperature, you can use the temperature reading of the conductivity probe to temperature compensate your pH readings. Again, it is very important to understand that this is going on and to make sure that you have that second sensor in both the buffer during calibration and in the sample during measurement. The last option would be to manually input your temperature value during calibration and measurement. I would only recommend this option if you are using a temperature-controlled bath where you're keeping the temperatures constant for both calibration and measurement. If you expect the temperature to vary from calibration and during measurements, it's best to supply the instrument with a temperature measurement so proper compensation can be carried out consistently and accurately. Now that you know temperature is important, be sure to periodically check your temperature sensor for accuracy. This can be done by comparing it to a NIST traceable temperature sensor. When comparing two temperature sensors, be sure they are close to each other, preferably with the thermistors touching each other, and the measurements should be within the two sensors' accuracy spec. For example, if one sensor has an accuracy spec of plus or minus 0.2 degrees C, and the other is plus or minus 0.1 degrees C, then the two thermistors should be reading within 0.3 degrees C of each other. Now that we covered what the calibration is actually doing to the system, and the importance of also measuring temperature, let's talk about what you can do to ensure you are calibrating your system properly. First, make sure you are using fresh, traceable pH buffers. At YSI, we recommend using traceable buffers to guarantee you are using a highly accurate solution. We don't want to introduce air to the system just by using an inaccurate solution for calibration. That would introduce air before we even got started. Just as important as using traceable buffers is making sure your solutions are fresh and not contaminated. Old or contaminated buffers will introduce error in your calibration and subsequent measurements. So check the expiration date on your bottle and note that buffers actually have two shelf lives, one unopened and one opened. For example, YSI buffers have a 2-year shelf life unopened, but once you open it, the shelf life is reduced to 6 months. So check with the manufacturer of your buffer solution to obtain this information and write the date you open the bottle, the buffer right on the bottle. Since transpiration or evaporation can affect buffers, make sure you close the bottles when you are done with them. If this becomes an issue, there are buffers available in larger airtight bags that will last longer. In order to avoid contaminating your buffers, make sure you thoroughly rinse your sensor with deionized water and blot dry with a chem wipe between calibration points. As a best practice in the lab, you should triple rinse with DI water between calibration points. Also, as a good laboratory practice, you should definitely not reuse buffers. Once buffers are used for calibration, they are assumed contaminated. Reusing buffers can lead to slow responding pH probe performance or the inability to calibrate at all. This reuse can also make it difficult to determine whether the probe or the buffers are actually causing the pH calibration failure. Once you have acquired your buffers, check your instrument to see if you have an auto buffer recognition feature. If you have this feature, select the buffer set that matches your buffers. Some instruments, like the YSI TrueLab, has over 20 different buffer set values pre-programmed in the instrument. If you can't find your buffer set, I suggest you turn off auto buffer recognition so you don't introduce error by calibrating to the wrong value. For example, NIST and NIST traceable buffers have different values, as you can see in this slide. It is also important to note that pH buffers are slightly temperature dependent, so the actual pH value of the buffer varies with temperature. For example, the actual pH of YSI buffer 7 at 20 degrees C is 7.02, and at 25 degrees C, it is 7.00. pH buffer values based on temperature can usually be found on the bottle or certificate from the buffer manufacturer. For maximum accuracy in your pH measurements, be sure that the auto buffer recognition is adjusting the buffer value based on temperature, or override the calibration value with the correct temperature adjusted value. All of YSI lab and field instruments have buffer values based on temperature pre-programmed into the instrument software in the auto buffer recognition feature, and these temperature corrected values are used. The next thing to determine is the number of calibration points you want to use. You must do at least a 1-point calibration, and if you're only going to do a 1-point, if you're only going to perform a 1-point calibration, make sure you're doing it with buffer 7. This will establish the intercept of the plot. However, with a 1-point calibration, a practical slope is not calculated. Instead, the meter uses the theoretical slope, which is 59.1 millivolts per pH unit. Because of this, a 1-point calibration should only be used when your expected measurement range is between 6.5 and 7.5. More common and most recommended is to conduct a 2- or 3-point calibration. I suggest doing a 2-point calibration if you know which side of the pH scale you expect to measure in. For example, if you know you are going to be measuring acidic samples, it is only required to calibrate at 7 and 4. In this example, calibrating at 10 will not improve your readings below 7. If you're not sure which side of the pH scale you will be measuring, then perform a 3-point calibration at 4, 7, and 10. Some meters allow you to calibrate up to 7 points for pH. Just make sure that you calibrate at buffer 7 for one of them, and that a second buffer differs by at least 2 pH units from the 7 in order to establish a good practical slope. Sometimes, depending on the instrument, the order you calibrate is important. Older instruments require you to start with buffer 7. Newer instruments allow you to calibrate in any order and calculate the intercept and slope after the calibration is complete. Just check with the instrument's operating manual to make sure you are following the manufacturer's recommended procedure. Next, make sure you are looking at the pH millivolts during calibration. Again, the pH millivolt value is the raw signal coming from the sensor that the instrument converts into pH units. Evaluating the millivolt value during calibration can help us document sensor aging and help us to determine if the sensor needs serviced, cleaned, or replaced. Evaluating the millivolt values will also tell us how good our calibration is or if we're nearing the outer edge of the acceptable limits. This can help us plan for future maintenance or replacement requirements. The acceptable values for the millivolt signal in buffer 7 is between -50 and +50. This is a general rule for all pH electrodes. Lab-specific electrodes or specialty electrodes may have a tighter recommended range for this, like the YSI TrueLine, ScienceLine, and IOLine electrodes, which have a millivolt range of negative to +30 when in buffer 7. The acceptable millivolt values for the other buffers depends on what the millivolt value is in the 7, because we are looking to establish a slope. In buffer 4, we are looking for a positive change in the millivolt value of 165 to 180, with 177 being the ideal. In buffer 10, we are looking for a negative change in the millivolt value of 165 to 180. For example, if we get a millivolt value of -10 in buffer 7, we would expect a millivolt value of 167 in buffer 4 and -187 in buffer 10. Most modern instruments store these values as part of a calibration record so it can be reviewed later. We will discuss the calibration record in a few minutes. There are several other things to consider when performing a calibration to ensure accurate measurements. You will want to make sure everything is clean so we don't contaminate buffer solutions. This includes the electrodes, temperature sensor, and calibration container. All should be cleaned and dry before starting. Next, make sure you are adequately immersing the sensing electrode, reference electrode, and temperature sensor into the buffer. We'll talk about this again in the next slide. Lastly, as a best laboratory practice, triple rinse the sensors and calibration container with deionized water between calibration points. Before continuing with the calibration, make sure to shake off any excess DI water or dry the sensor and container with a chem wipe before placing it in the next buffer. When drying the sensor with the chem wipe, be sure to blot it so you don't accidentally damage the sensor. When placing a sensor in either a buffer for calibration or a sample for measurement, make sure you first remove the storage cap from the tip of the sensor. The storage cap is provided for storing the electrode during shipment and long-term storage. I consider anything 3 weeks or longer to be long-term storage. For field probes, we'll talk about storage of lab probes shortly. The storage cap is filled with solution to keep the electrode from drying out and to slow the outflow of electrolyte. The solution used varies by manufacturer and electrode, but is usually KCl solution, buffer 4, or a mix of the two. Next, if using a refillable electrode, make sure the fill hole is open for both calibration and measurement. This is very important and a commonly missed step, especially if using a refillable electrode for the first time. Next, if using a refillable electrode, make sure the level of the reference electrolyte is higher than the level of the buffer or sample. The reference electrolyte should be at least 2 centimeters above the level of the solution that you're measuring or calibrating in. If it isn't, refill the electrode with 3 molar KCl or the electrolyte used by your sensor. Next, as mentioned before, make sure the sensing electrode, reference junction, and the temperature sensor are all immersed in the solution. To accomplish this, it's important to know the physical characteristics of your sensor, like where the reference junction and temperature sensor are located. If you don't know where they are, you can't guarantee they're in solution, so take a moment to get familiar with your sensor. As you can see in this picture, the reference junction location is dependent on the sensor that you're using. As mentioned before, many meters save calibrations in a GLP file or good laboratory practice file. The number of calibrations stored by a meter is instrument dependent, so check with the operations manual if you're unsure how many records your instrument is saving. Many instruments will allow you to back up the GLP data to a PC, to a computer, or may provide you the ability to print it out. Typically, the information stored in a GLP record includes the number of calibration points, the buffer values used during calibration, and the millivolt value from the sensor at each calibration point. Some meters will calculate the slope and electrode efficiency for you as well. The electrode efficiency is the actual slope divided by the theoretical slope from the Nernst equation, and then multiplied by 100 to give you a percent value. As the efficiency nears 90% or lower, you should consider servicing the sensor. That is, of course, after making sure you're following all the necessary steps to ensure a proper calibration. We don't want to service the electrode if it isn't necessary, so start by troubleshooting and verifying your calibration by verifying the buffers and the routine that you're using. Some instruments evaluate the GLP information for you and provides the status of the calibration. For example, some instruments will tell you that the calibration is questionable or out of range and should not be accepted. Other instruments, like the Multilab and TrueLab, will show how close the sensor's calibration is to the ideal, both in the calibration record and on the display during measurements. As shown in this chart, the more plus marks you have in the calibration record, or the number of dashes you have on the electrode icon in the display mode, will indicate to you how close you are to the ideal theoretical values in the Nernst equation. GLP records can be useful in helping track the sensor's performance to determine when refilling, cleaning, reconditioning, and/or replacement may be necessary. A common question we are asked is, how often should I calibrate my sensor? This is probably the most difficult question we get because there is no simple answer. Calibration frequency depends on the application and the age of the electrode. Being an electrochemical sensor, a pH sensor drifts over time due to its design and how it operates. This is why we must recalibrate. Older sensors tend to drift from calibration faster than newer sensors, so older sensors will require more frequent calibrations. More frequent calibrations will also be required when the application requires it. This could be due to applications that may cause the sensor to drift faster, such as samples that are heavily contaminated, have low ionic strength, are strongly acidic, or when the electrodes are used in higher temperature samples. Additionally, some applications may require a higher accuracy or precision than others. In that case, the sensor should also be calibrated frequently. I suggest, as a best practice, start by calibrating the system every day you use it. If you find, for example, that you are using the system every day and the sensor is holding its calibration adequately for you for 2 or 3 days, then you yourself may decide to only calibrate every 3 days. Another example would be if you're only using the instrument once per week. In that case, I would definitely perform a calibration before each use. Generally, a new electrode could hold its calibration for a week or more, while an aged electrode may drift out of calibration within 24 hours. If you are worried about forgetting to recalibrate, look for an instrument that provides a recalibration prompt or timer based on user-selected criteria. This can help remind you when it's time to recalibrate your system. Now that we've reviewed how to perform a proper calibration, let's review maintenance tips for pH electrodes. If you're having issues with calibration or if the electrode is slow to respond, performing maintenance such as cleaning, refilling, and reconditioning can be used to help bring the electrode back into spec and extend its usable life. Slow response is application dependent, but I would say if it takes the probe longer than 2 minutes to go from 7 to 4 or from 7 to 10, then the response is less than ideal and electrode maintenance should be performed. Non-refillable electrodes do have a finite usable life. Generally, a non-refillable electrode will need to be replaced every 18 to 24 months due to a reference electrolyte leaching out and not being able to be replaced. If you are having slow electrode response or difficulty calibrating, try cleaning the electrode. We will go through the cleaning steps in a moment, but here are some quick precautions on cleaning. First, you will always want to recalibrate after cleaning. Remember, your data is only as good as your calibration. Next, rinsing in DI water is part of the cleaning process and, in fact, also part of the calibration process we reviewed. Even though we recommend rinsing in DI water, it is very important to note that a pH sensor should never be stored in DI water. As a general rule for pH electrodes, it is best to perform a chemical cleaning on the electrode and not a mechanical cleaning. The reason for this is because with a mechanical cleaning, there is greater risk of damaging the electrode, and the damage may very well be irreversible. Also, please note that we have different cleaning recommendations for field and lab pH electrodes. I'll be reviewing recommendations for lab electrodes in today's presentation. For information on cleaning field sensors, please review our pH handbook or our previously recorded webinar on pH field measurements. If you see poor pH electrode performance and you suspect inorganic contamination, place the probe in 0.1 molar hydrochloric acid or 0.1 molar sodium hydroxide for about 5 minutes. If this does not clean the electrode, try heating the solution to 50 degrees C and then soaking the electrode. If you suspect organic debris, rinse the electrode with an organic solvent such as ethanol or acetone. Before doing so, check the chemical compatibility between the solution you want to use and the sensor's body material, and make sure there aren't any issues with using the two together. You might need to delete your organic solvent or select a different organic solvent. Oh, I went ahead of slide. Sorry, everybody. There we go. Oh, never mind, the slide's missing. Sorry about that. Well, we'll get you guys the PDF of this. So I'm speaking about the slide that's missing with organic debris and inorganic debris. But you can picture what I'm saying. So after if you suspect organic debris, rinse the electrode with organic solvent such as ethanol and acetone. And as I mentioned, make sure there aren't any chemical compatibilities between the solution that you choose, the strength of that solution, and the body of the electrode that you're trying to clean. So, you know, take some time to make sure that you're not going to use anything that's going to degrade or eat away at the body of your probe. Next, carefully wipe the glass bulb with a chem wipe or other lint-free soft cloth. Now on to proteins. If you suspect the junction is clogged from proteins, try soaking the electrode in a pepsin hydrochloric acid solution for at least 1 hour. After performing any of the discussed cleaning procedures, thoroughly rinse the electrode with DI water, then soak it in 3 molar KCl for at least 1 hour before attempting a calibration. Soaking in 3 molar KCl, potassium chloride, can also help rejuvenate a reference junction that has accidentally dried out. Because I know no one's going to let it dry out on purpose, right? If you have a refillable pH electrode and you find that the reference electrode has been contaminated, it is very necessary that you remove all of the electrolyte from the refillable sensor and replace it with fresh electrolyte. Do not try to rinse the electrolyte reservoir with anything but fresh electrolyte. You may need to repeat this step several times until all the contamination has been removed from the reservoir. If the KCl has formed crystals in the reservoir, you can dissolve them by heating the electrode in a 45-degree C water bath. Be sure to drain and replace the electrolyte after doing this. It is very normal for KCl crystals to develop on the storage cap, electrode, and around the filling hole during storage. New electrodes may also have salt crystals. This is normal, and they can be cleaned off by rinsing with DI water and wiping with a lint-free cloth. Next, I would like to discuss how to properly store laboratory pH electrodes. Electrode storage is very important to extending the life of the electrode and electrolyte. If not stored properly, a pH electrode can be permanently damaged. We have 2 different storage recommendations based on how long you plan to store your lab electrode. I will review these in the next slide. Some helpful tips for all pH electrodes, whether lab or field, is to make sure that you never let your pH electrode dry out and never store your electrode in DI water. When storing lab electrodes between measurements, place the electrode in a 3 molar potassium chloride solution. Be sure to rinse the probe with some sample or DI water before placing it back into the sample for measurement. So after you pull out of storage, make sure you rinse it before you put it into a sample. You don't want to carry over any KCl into your sample. Also, as we have mentioned before, make sure the refill hole is open during measurements. If you are storing your lab probe overnight or longer, make sure it is clean, and then fill the storage cap with 3 molar KCl and install it over the sensor. Be sure to close the refill hole during storage so the electrolyte does not evaporate during storage time. As mentioned, you can try to recondition your probe, your electrode, if cleaning does not bring it back into spec or improve the response. Field electrodes can be soaked in buffer 4 overnight or over the weekend to try and rejuvenate them. Lab electrodes can be soaked in 3 molar KCl. If good calibration, slope, or response is not restored after cleaning and reconditioning, it's probably time to replace your sensor. Now I'd like to turn it back over to Chris so he can review some tips on how to select a benchtop lab meter that best meets your application requirements.
Thanks, Laura, for those practical pH tips. Now I'd like to briefly discuss some things to consider when selecting a pH meter. The question I would first ask yourself is if you want to only measure pH and temperature, or if there are other parameters you would like to measure. There are pH-only instruments on the market, such as our YSI TrueLab 1310, as well as instruments that have the ability to measure many parameters, such as the YSI Multilab series of instruments. By asking this question first, you will help narrow your search for a new instrument. The next question to ask is the number of measurement channels you would like. A measurement channel is basically an input for a sensor, so one measurement channel instrument will only allow one sensor to be connected, and one measurement will be displayed on the instrument in addition to temperature. The Multilab 4010-3 is a 3-channel instrument, so the user can connect 3 different sensors, such as a pH sensor, a dissolved oxygen sensor, and ammonia sensors. After narrowing your search based on parameters and the number of channels, I would further narrow it by considering the type of sensor connection you need. BNC is perhaps the most common type of connector. One major advantage to this sensor is how universal it is. Typically, BNC electrodes can be connected to any pH meter with BNC input, regardless of the manufacturer. So another manufacturer's BNC electrode can be used on our TrueLab, and our BNC pH electrodes can be used on other manufacturers' BNC pH instruments. Another common type is the digital connector. These are specific to each manufacturer, so they don't have the same flexibility as BNC pH electrodes. However, there are major advantages to a digital connection, as these sensors store their calibration data and their serial number. They are also auto-recognized when connected to the meter, so there is no need to tell the instrument what is connected. Our Multilab 2 and 3 channel instruments are digital, but they also allow the connection of a BNC electrode if a BNC adapter is installed. This allows the user to connect both digital and BNC pH sensors. Another major thing to consider is how you will be recording your data. If you simply write the pH measurement in a notebook and that is all you need, then there is no need to search for an instrument with a large memory. On the other hand, if you would like to save data to the instrument, back up data to a USB flash drive, and send data straight to Microsoft Excel, there are instruments with these advanced data management options. Some instruments can also come with an optional printer if your lab procedures do require one. The instrument display quality should also be considered. Some instruments have a very basic display, while others have a large, backlit graphic display with color. These instruments can clearly be seen from across the room, which is very helpful if you are preparing solutions and you want to keep an eye on the displayed measurement. Therefore, you will want to ensure the display is easy to see and will meet your needs. Now that you have a meter selected, ensure it has other important features before making a purchasing decision. Auto buffer recognition speeds up calibration by automatically recognizing the buffer being used. Automatic temperature compensation is very important, as this feature takes the temperature reading and automatically compensates pH measurements for the influence of temperature. A detailed calibration record, also called a good laboratory practice record, allows the user to view important calibration information such as the slope, 0 point, millivolt values in each buffer, and temperature for each calibration point. Also consider what is included when you purchase the meter, such as an electrode stand, power supply, and other accessories. Some instruments have many stored buffer sets within the instrument's memory. Since buffer sets can have different temperature profiles and buffer values, selecting the exact buffer set you have will ensure an accurate calibration result. Since lab instruments should last a long time, please consider the meter warranty period and the quality of the company's technical support. This will be very important if you ever have an issue with the meter. Also ensure the meter has a variety of pH electrodes available and that the meter is easy to use. This can be done by checking out reviews, a video overview of the meter, as well as other videos where the meter is actually being used. Instrument auto-stable will ensure calibration and measurement points are not recorded until the measurement is stable. So this is another important feature to consider. Finally, ensure the meter can display millivolt values, as this is an excellent troubleshooting tool when trying to determine any electrode issues. I would like to wrap up this presentation by discussing some helpful pH resources we have available. Perhaps the most comprehensive resource is the YSI pH Handbook. Much of the information covered today is included in this handbook, although it is discussed in much more detail. At the back of the handbook, the most practical points are summarized in the pH Quick Tips section. These pages can be printed and hung on a wall in your lab as a quick reference. We also have a calibration guide that discusses the most important aspects of calibration, as well as the electrode selection and application guides we saw earlier. Finally, we have a variety of helpful videos on our YouTube channel, and we cover many lab-related topics on our blog and in our lab newsletter. With that, we would like to answer some of the questions participants and listeners have sent in.
Okay, our first question is, why is it so important for the refill hole to be open during calibration/measurement?
That's a great question, and thank you, Teresa. So it is important the refill hole is open because this allows electrolyte to flow out through the junction. Otherwise, if it is closed, due to pressure, electrolyte will not flow out through the junction.
Okay, our next question is, why did YSI recently change the recommended storage solution from either pH buffer or 2 mole KCl solution to just KCl?
Great question. Thank you for that. It really just depends on the electrode itself. We ship electrodes stored in different things. Some of our field electrodes are stored in buffer 4. Some of our field electrodes are stored in a mix of buffer 4 and 3 molar KCl, and then our newer lab line, they're all stored in 3 molar KCl. They all perform the same function, which is keeping the reference saturated and keeping the reference from drying out. To keep the electrolyte from leaching out faster. So it's all about creating kind of a barrier, storing it someplace where there's where it's not going to pull out electrolyte faster than we would want it to. So they both provide the same function. Great question.
These are great questions. Keep them rolling in. Our next question is, do you recommend stirring while taking readings? And, oh, I'm sorry, I started on the wrong one. Is it okay to touch the bulb with anything but a chem wipe so you don't disturb? There's like a layer of hydration. So if you touch it with a chem wipe, is that going to disturb that layer of hydration?
That's a really good question. Chem wipes are okay to use on lab and field, but you have to be really careful with it because a chem wipe can actually scratch the glass bulb. So you can blot dry with a chem wipe, but I would never wipe with a chem wipe. Just very gentle blot with that. But that's a very good question, though.
Okay, what is the ideal range of the slope for 3 points? 4, 7, and 10 for pH calibration.
Good question. The ideal slope, according to the Nernst equation, is 59.1 millivolts per pH unit. So that comes out to roughly 177 between 7 and 4. So you want a change of about 177 millivolts positive between where you are in the 7 and where you are in the 4. And then you want a negative change of 177 millivolts between your value at buffer 7 and your value at buffer 10. So you're looking for a negative change to buffer 10 and a positive change to buffer 4. The millivolt, the idea of millivolt, the idea of zero, offset, or intercept, we've referred to it all the same. So the idea of millivolt value for buffer 7 for a field probe is generally between negative 50 and positive 50, and between negative 30 and positive 30 for a lab probe. Good for a lab electrode. Good question.
Great. Is it necessary to move the pH probe around in the solution while it is stabilizing?
So that's another really good question. For pretty much any lab analysis, it's going to be best to have stirring. So to use a stir plate, for example, like with ion selective electrodes, which pH is an example, one of those, standard methods typically calls for stirring. So Usually for best lab practice, it is best to stir, but you don't have to do it.
Do you recommend 2 centimeters below the opening hole for KCl solution?
So the electrolyte can be filled all the way up. There's no issue with that. The biggest thing with the level of electrolyte is it does have to be at least 2 centimeters higher than the measurement solution itself. So really there's no issue with just completely filling up the electrode with a reference electrolyte. In fact, that's probably a good procedure to just go ahead and do. But yeah, there's no issue with that. So good question.
Okay. Are there any lab pH probes that are all-in-one with a preamp, like a field pH probe, so that you do not need the bulky meter?
Good question. So we do have amplified pH probes available for the field. And you know, the big reason behind having an amplified pH probe is to boost or amp the analog signal coming out of the pH electrode. So we would recommend it in older analog field instrumentations that have really long cable runs or have older connectors that could be contaminated. So our handhelds that are analog are like the Pro Plus and the 556. In those instances, that analog signal from the pH probe has to run all the way back to the meter before it's converted to a digital readout for you. So if you're running 20-meter cables or longer, or if your instrument is old and the connectors are dirty, you're having a hard time keeping them clean, an amplified probe can help overcome those. So amplified probe helps increase an analog signal to go long cable runs and to get around any contaminated or wet connectors. In the laboratory, we have digital instruments, so they are digital sensors. So the analog signal is really going a short distance from the tip of the electrode right to the PCB, the PC board in the probe itself. So the analog signal travels a very, very short distance and then is digitally sent up to the instrument. So amplified isn't required in that application. And for our analog instruments, again, we're talking about 1 meter of cable between the analog signal and the instrument that changes it from an A to D. And we have small benchtop instruments that do that conversion. So we haven't seen it necessary in a laboratory example, in a laboratory application. Thanks, great question.
So we store the electrode in pH 7 after calibration prior to testing. How long would be too long to leave the electrode in pH 7?
So keeping it in pH 7 will be just fine for a really long time. One thing I would recommend doing is if you're storing it in pH 7, I would add some 3 molar KCl because that's just going to create the best environment for storage. But as far as 3 molar KCl itself, it should have a pH around 7 anyways, so you should be just fine to leave it stored in pH 7 buffer.
Yeah, I would agree with Chris. We do have people that store in their electrodes long-term in pH 7. You know, there's a lot of options. Our best recommendation for field probes is buffer 4 because it's readily available. Buffer 7 can work as well. If you're in a bind, environmental water or tap water, just really stay away from DI water.
There's some wonderful questions. Thank you so much. Unfortunately, we are going to have to end today's webinar, but we will follow up with you directly. If you had a question that was not answered, we will follow up directly to answer your question. So thank you again for all your great questions. And thank you for attending today's webinar. We hope that you found all this information useful. Please complete the brief survey at the end and let us know how we can better serve you. We really appreciate all the great questions. Unfortunately, we couldn't get to them, but we will follow up with you. So thank you again, and we hope to see you next time. Thanks.